Stop getting stuck in optimization problems. Try simulated annealing instead. Simulated annealing mimics the cooling of metals to find the best solution in a sea of possibilities. Think of it as a smart way to explore vast landscapes and avoid getting trapped in valleys of suboptimal solutions. Here's how it works. We start with an initial solution and a high temperature. At first, the algorithm accepts even worse solutions to escape local traps. This is like taking a few risks to find better paths. As the temperature drops, the algorithm gets pickier, zooming in on the best solution. The cooling schedule, linear, exponential, or logarithmic, determines how fast we cool down, impacting our success. So next time you face a tough optimization problem, remember, simulated annealing. It's like having a map and a torch in a dark maze. Keep watching to see it in action with a real-world example.
Simulated annealing. Simulated annealing is a stochastic optimization algorithm that is often used to find the global minimum or maximum of a non-convex function. The algorithm is inspired by the process of annealing in metallurgy, where a metal is heated and then slowly cooled to reduce its defects and improve its properties. The algorithm starts with an initial solution and temperature, and then iteratively generates a new solution by perturbing the current solution. If the new solution is better than the current solution, it is accepted as the new current solution. If the new solution is worse than the current solution, it is accepted with a certain probability that decreases with the temperature. This allows the algorithm to escape local minima and explore the search space more thoroughly. The probability of accepting a worse solution is given by the metropolis. Hastings' algorithm, which is a probabilistic algorithm for generating samples from a probability distribution, the algorithm calculates the change in the objective function between the current and perturbed solution, and then calculates the probability of accepting the new solution as follows. Let's get coding. Import numpy as np. Import random. Import math. Import matplotlib. Define the objective function to be optimized. Def objective function, params. This function defines the objective function to be optimized. It takes a parameter array, params, and returns the value of the objective function. Args. Params, numpy, and array, an array of parameters to evaluate the objective function on returns. Float, the value of the objective function evaluated at params. X, I, U, Z, params, zero. Paramsron, params2. Return, X4, 22EY5, 2ZU62. Define the ranges of the input parameters. Xrange, IU, and P. Arrange, 10, 0.1. Range UNP. Arrange, 10, 10, 0.1. Ztrange, EEETEA, and 10, 0.1. Create a mesh grid of the input parameters. X, I, U, Z, LP. Mesh grid. Xrange, Zrange, indexing, IG. Calculate the objective function value for each point in the mesh grid. Objective MP, zeros. Len, Xrange. Len, Ythrange. For I in range, len, Xrange. For J in range, len, Urange. For key in range. Objective E, J key, she, D, objective of function. I, yud, the ranges, U to range, Z. IU create a contour plot of the objective function. Fig, X, P plot, subplots. CEAX, contour, X, 0, UUI, 0, objective, 0, plot, color bar. X, sex label, X. X, set label. X, set a title, objective function contour plot. Pulled, show. Define the simulated annealing algorithm. Def simulated annealing, Abschwung, bounds in it to final cooling trait. This function implements the simulated annealing algorithm to optimize the objective function. It takes the objective function parameter bounds initial temperature in it final temperature and coolant rate as inputs. Art. Object function. The objective function to optimize. Bounds numpy and array, an array of parameter bounds. Each row represents the lower and upper bounds for a parameter. Float, the initial temperature. Typhonal, float, the final temperature. Cooling rate, float, the coolant rate. Returns. Tuple, a tuple containing the final parameter array, the final objective function value, and a list of temperatures. You initialize the current solution and temperature. Num params at bounds, shape 0. Current params I, A, and P. Array, random. Uniform, bounds 0, bound 0. Bound siam range, num params. Nummel params. Current solution G of G func su. Current params. T current EET in it. Temperatures. Iterate until the temperature is below the final temperature. Wild to current IT Tephanol. IU randomly perturb the current solution. Perturb to params. IU AU CMP. A random. Uniform, bound size 0, bound xi, arm ring. For I in range, nummel params. Perturbed solution perturb. You calculate the change in solution quality. Delta E perturbed solution. Current solution. If the perturbed solution is better, accept it as the new current solution. If delta she 0. Current params perturbed params. Current solution E perturbed solution. If the perturbed solution is worse, accept it with a certain probability. Else. Probability etchi math. X. Delta et tar current. If random. Random. Probability. Current params perturbed params. Current solution E perturbed solution. E decrease the temperature according to the cooling rate. To current E cooling rate. Temperatures. Append. Turrent. To return the final solution and its quality and the list of temperatures. Return current params current solution, temperatures. Def plot cooling rates. Objective function, bounds tessinit to final cooling rates. Plots the temperature versus iteration for different cooling rates in the simulated annealing algorithm. Args. Objective function. The objective function to be optimized. Bounds and array. I and N x2 numpy array where N is the number of parameters. And each row contains the lower and upper bounds for a parameter. The initial temperature. Final float. The final temperature. Cooling rates. List. A list of cooling rates to be tested. Returns. None. Initialize a dictionary to store the final solutions and qualities for each coolant rate. Results. Iterate through the cooling rates and run the simulated annealing algorithm with each one. For cooling rate and cooling rates. Final solution, final quality, temperature simulated annealing, objective annealing. Objective function, bounds, tighten it. Final cooling rate. Print. Result for cooling rate T cooling rate is results cooling rated solutions. Final solution quality, final quality, temperatures. Temperatures. Print. The correct solution is XC4, YU5, and ZU. 6 for our objective function. X4, 2 UEY, 5, 2, ZU6, IT2. Print. Plot the results for each cooling rate on a single plot. Fig AXU plot. Subplots, fig size, 10, 6. For cooling rate and cooling rates. Temperatures results cooling rates temperatures. Quality SE results cooling rates. X. Plot. Temperatures. Label of cooling rate quality. X. Sets label. Iteration. X. Set the label. Temperature. X. Set a title. Temperature versus iteration for different cooling rates. X. Legend. Apply, show. Bounds HNP. Array 10, 10, 10, 10, 10, 10. In it to final cooling rate E100 0.1, 0.95. Cooling rates IF 0.2, 0.5, 0.6, 0.8, 0.9. Plot cooling rates, objective function, bounds, tie-in. The results from running the simulated annealing algorithm with different cooling rates can tell us about the trade-offs between exploration and exploitation in the optimization process. A slow cooling rate, e.g., 0.99, allows the algorithm to explore a larger portion of the search space, potentially finding global or near global optima, but this can come at the cost of longer running time. On the other hand, a fast cooling rate, e.g., 0.2, can lead to exploitation of local optima and faster convergence, but may miss global optima if they exist in unexplored regions of the search space. In general, it's important to balance the rate of exploration and exploitation based on the problem at hand. If the search space is large and complex, a slower cooling rate may be more appropriate to allow for thorough exploration. However, if the search space is relatively small and simple, a faster cooling rate may be more appropriate to quickly converge to a high-quality solution. Import numpy as np. Import matplotlib.pyplot as plt. From mpl_toolkits.mplot3d import axis 3d. Import matplotlib as mpl. Define the objective function. Def objective xy. Return np.sin x np.cows y. Def objective xy. Objective function to be minimized. Args. X float the x input value. Y float the y input value. Returns. Float the objective function value. Return -np.xp-0.2x22y22 0.5 np.xp-0.2x2y22. Set up the grid. xnp.linspace-10 10 100. ynp.linspace-10 10 100. X ynp.meshgrid xy. Compute the objective function on the grid. Z objective xy. Create the 3D plot. Fig plt.figure fig size 1210. axfig.add _subplot 111 projection add d. Plot the surface. Surf ax.plot _surface xyz cmap coolwarm alpha 0.8. Add a color bar. Fig.colorbar surf shrink 0.5 aspect 5. Set the axis labels and title. ax.set _x label a. ax.set _y label a. ax.set _z label a. ax.set _title objective function. Show the plot. plt.show. Let us find the maximum in this case, not minimum like we normally do with optimization. It just involves changing the sign in the exponent of the acceptance probability and also looking for the highest candidate score and not the least. See comments in the code below. Define the simulated annealing algorithm function. Def simulated _annealing _3D objective _funcs bounds cooling _rate max _iterations. Simulated annealing algorithm for finding the global minimum of an objective function. Args, ne as in noun. Objective _func function, the objective function to be minimized. Bounds numpy.end array, a 2D array of shape n2 that defines the bounds for each input parameter. Cooling _rate float the cooling rate for the annealing process. Max _iterations int the maximum number of iterations to perform. Returns. Tuple a tuple containing the solution history and score history for each iteration. Initialize the solution with random values within the bounds. Solution np.array np.random.random.uniform low, high for low, high in bounds. Calculate the initial objective function value. Best underscore score objective underscore func solution. Initialize the temperature. Temperature 100.0. Initialize the list of scores and solutions. Score underscore history best underscore score. Solution underscore history solution. Run the simulated annealing algorithm. I in range max underscore iterations. Generate a new solution by randomly changing one parameter. Candidate solution np.random.normal size len bounds. Ensure the candidate solution is within the bounds. Candidate np.clip candidate bounds 0, bounds 1. Calculate the objective function value for the candidate solution. Candidate underscore score objective underscore func candidate. Calculate the acceptance probability based on the temperature. Add a negative sign to the exponent if searching for minimum rather than maximum. Acceptance underscore prob np.xp candidate underscore score best underscore score temperature. Decide whether to accept the candidate solution or not. Change for best underscore score to if searching for a minimum. If candidate underscore score best underscore score or np.random.rand acceptance underscore prob. Solution candidate. Best underscore score candidate underscore score. Reduce the temperature based on the cooling rate. Temperature cooling underscore rate. Append the best score and solution to the history lists. Score underscore history dot append best underscore score. Solution underscore history dot append solution. Return solution underscore history, score underscore history. Define the bounds for the input parameters. Bounds np.array-100, 10, -10, 10. Set the cooling rate. Cooling underscore rate 0.95. Run the simulated annealing algorithm. Solution underscore history, score underscore history simulated underscore annealing underscore 3D objective, bounds, cooling underscore rate, 1000. Create a 3D mesh grid for the input parameters. Fig plt.figure fig size 1210. Ax fig.add underscore subplot 111, projection ed. ax.plot underscore surface xyz, cmap viritis, alpha 0.5. Plot the solutions found by the algorithm for each iteration. For I in range len solution underscore history, xy solution underscore history I, z score underscore history I. ax.plot xyz row, alpha I len solution underscore history. Set the axis labels and title. ax.set underscore x label a. ax.set underscore y label a. ax.set underscore z label objective. ax.set underscore title emulated annealing 3D. Show the plot. plt.show. And that's how simulated annealing can help optimize complex problems. I hope you found this video informative and enjoyable. If you did, please give it a thumbs up and don't forget to subscribe to our channel. Your support helps us create more content like this. Also, hit the notification bell so you never miss an update. We have more exciting topics and tutorials coming your way. Thank you for watching, and we'll see you in the next video. Happy optimizing!